Thank you for attending tonight's session. In this lecture, we're going to continue on with time series analysis, and we want to talk about two different techniques within time series analysis: moving averages and exponential smoothing. This chapter introduces models applicable to time series data with seasonal, trend, or both seasonal and trend component, and stationary data. Forecasting methods discussed in this chapter can be classified as averaging methods, where you can see there's two different ones, equally weighted, different weights. And the second category is exponential smoothing methods, unequal sets of weights to past data. Now, under the exponential smoothing methods, all methods in this group require that certain parameters be defined before you perform the analysis. These parameters, with values between 0 and 1, will determine the unequal weights to be applied to past data. Let's begin with averaging methods. If a time series is generated by a constant process subject to random error, then the mean is a useful statistic and can be used as the forecast for the next period. Averaging methods are suitable for stationary time series data where the series is in equilibrium around a constant value. This is the mean, with a constant variance over time. Exponential smoothing. The simplest exponential smoothing method is the single smoothing method, SES, where only one parameter needs to be estimated. There are other exponential smoothing methods, but we won't cover them in this class. We will only cover the basic, the single smoothing method. If you understand that, then the other methods aren't much more difficult or complicated than the single smoothing method. Let's go into detail now about the averaging methods. So let's look through these boxes, starting at the orange box on the top left and continuing in a clockwise manner. The moving average for time period T is the mean of the n most recent observations. So n can be 3 for quarterly, 6 for semi-annually, or 12 for annual data. N is the time periods you are looking at. The constant number n is specified at the outset, at the very beginning. The greater the number n is, the less weight is given to more recent periods. The smaller the number n, the more weight is given to recent periods. The mean uses the average of all historical data as the forecast. When new data becomes available, the forecast for time t plus 2, 2 periods in the future, is the new mean, including the previously observed data plus this new observation. So you can see on the formula there, it's just a simple mean calculation, but now it's for forecasts 2 periods in the future. The mean is appropriate when there is no noticeable trend or seasonality in the data. A moving average of order k, moving average k, is the value of k consecutive observations. Now, let me point out that k is equal to capital N, which is equal to lowercase n. These are the numbers of observations, and k, n, capital N, and little n are used interchangeably. It's like car and automobile. They mean the same thing. K, capital N, lower n is the number of observations. The moving average model does not handle trend or seasonality very well, although it can do better than just the total mean. A large N, or K, is desirable when there are wide, infrequent fluctuations in the series. A small n is desirable when there are sudden shifts in the level of the series. For quarterly data, a 4-quarter moving average 4, eliminates or averages out seasonal effects. For monthly data, a 12-month moving average, MA12, eliminates or averages out seasonal effects. In a moving average 12, the N is equal to 12. The number of observations is equal to 12. Equal weights are assigned to each observation used in the average. Each new data point is included in the average as it becomes available, and the oldest data point is discarded. So you can see there the formula for a simple moving average. Again, it's just the mean over whatever time period you use, whatever N or K that you choose to study. When simple moving average models are employed, the forecast model is ft plus 1, that's the forecast. So we're going to take a simple moving average and use that as a forecast for one period into the future. And you could see there in the blue box that f subscript t plus 1 is the forecast for the next period. So let's try an example here. So we have patient arrivals week 1, week 2, week 3. 400 in week 1, 380 in week 2, 411 in week 3. The average for those 3 weeks is 397. So that's our forecast for week 4. The forecast error for week 4 is 415 minus 397. And the question is, where did that 415 come from? Okay. That's shown here on the next page. But those are patient arrivals for week 4. So the 415 is given. The error between the actual of 415 and the forecasted of 397 is 18. If we want to make a forecast using simple moving averages for week 5, then we're going to take the data for weeks 2, 3, and 4. Remember that week 4, the number of patient arrivals was 415. So the forecast for week 5 is 402 patient arrivals. Again, it's a one step ahead forecast. So we take the average of weeks 2, 3, and 4. We come up with the average, which was 402. The forecast for week 5 is 402 patient arrivals. Let's try a longer example here. So the weekly sales figures in millions of dollars presented in this table are used by a major department store to determine the need for temporary salary personnel. So you could see in the first column, it's the period. In the second column to the right, those are the sales in millions for each corresponding period. Here's a graph of what that table looks like. We want to use n is equal to 3. That was somewhat arbitrary as we chose that. But we want to then use n is equal to 3 for department store sales for the weeks 24 and 26. So the forecast error, in week 24, we forecasted 5.9. It was actually 6. So week 24, you can see the 6 there at the bottom. We forecasted 5.9. So the error is 0.1. The forecast for week 26 is the actuals for week 25, week 24, week 23. The average is 5.7. It's really 5 2/3, but we'll round that up to 5.7. So using the actuals from periods 25, period 24, and period 23, we forecast sales in period 26 to be 5.7 million. You can see here then that we've added a column to this spreadsheet, and it has now the forecast for sales. So again, when we look at period 26 here, it's 5 2/3. It's actually these numbers that went into this calculation. It was rounded up to 5.7. But the sales for periods 25, 24, and 23 were averaged to determine the forecast for period 26. Next, we want to move into exponential smoothing models. So this method provides an exponentially weighted moving average of all previously observed data. Exponential smoothing is appropriate for data with no predictable upward or downward trend. The aim is to estimate the current level and use it as a forecast for future value. Here is the equation then for exponential smoothing. So ft plus 1, that's the forecast one period into the future. Alpha is the smoothing constant. Yt is the current observation ft is the current forecast. So we want to take a combination of the smoothing constant, the current observation, and the current forecast to give us a forecast one period into the future. The forecast, t plus 1, is based on weighting the most recent observation yt with a weight alpha and weighting the most recent forecast ft with a weight of 1 minus alpha. So in the equation, alpha, 1 minus alpha, they represent weights. So here is exponential smoothing expanded out based off substitutions. The purpose of this graph is to show you the inner mechanics on how this equation was derived. I think basically this is the same graph. And again, it's giving you a derivation of how the exponential smoothing model was arrived at. So it's a continuous substitution process. You keep substituting in, and here's the full equation. Therefore, the forecast one period into the future is a weighted moving average of all past observations. And again, here's the equation right here. We want to forecast one period into the future. That's what ft plus 1 is. You can see the alpha there. So alpha is going to be critically important in exponential smoothing. The exponential smoothing equation, rewritten in the following form, elucidates the role of the weighting factor alpha. This blue area is important. The exponential smoothing forecast is the old forecast plus an adjustment for the error that occurred in the last forecast. So exponential smoothing forecast is the old forecast, but we make an adjustment for the error that we made in the last forecast. The value of this smoothing constant must be between 0 and 1. It cannot be 0 or it cannot be 1. It has to be 0.001 or 0.9999. Those are the two lower and upper limits. If stable predictions with smooth random variation are desired, then a small value of alpha is appropriate. Alpha could be 0.1, 0.2, 0.25. That applies to stable predictions. If rapid response to a real change in the pattern of observations is desired, a large value of alpha is appropriate. So alpha could be 0.75, 0.8, 0.95. The greater the alpha, the more rapid the response is in the forecast. To estimate the alpha, the smoothing constant, forecasts are computed for alpha equal to 0.1, 0.2, 0.3, all the way to 0.9. And the sum of the squared errors is computed for each. the value of alpha with the smallest mean squared error is chosen in producing the future forecasts. So again, we want to compare the actual to the forecast, which alpha gave us the smallest prediction area. That's the alpha that's most appropriate for you to use in your exponential smoothing. And again, that bottom graph is very descriptive. Why do we use this exponential model? Because decreasing weights, lesser priorities are given to older observations. The most current observations get the greatest weight. Past observations, long past, are given smaller weights. So that is the rationale behind the exponential smoothing method. So here's a table. I didn't finish it out, but you can see then that you do these types of calculations, and in the weights, you go out there, run the numbers, and you can see what the weights are for past periods based off the alpha assigned to your exponential smoothing. So this is just the math. Let's assume then that we've calculated the alpha that we are most satisfied with. So to get this process or the algorithm started, we need a forecast for the first period, because you can see the forecast for period 2 is based off the forecast for period 1. Since we don't know what the forecast for period 1 is, there are a couple things that we can do. Set the first estimate equal to the first observation. Second, we can use an average of the first 5 or 6 observations for the initial smooth value. But we have to determine the first forecast to get this whole process started. So those are a couple suggestions on how to get this process started. Let's look then at the University of Michigan Index of Consumer Sentiment. So between January 1995 to December 1996. We have observations between January 1995, December 1996. We want to forecast what the consumer sentiment will be for January 1997. There is no forecast available for the first period, so we'll just keep it simple and we'll use the first observation as the first period. A couple of different alphas that we will try is alpha equal to 0.3 and 0.6. And why we made that choice, totally arbitrary. In reality, you should probably try many more alphas than just 2. You can see then that the last 2 columns are forecasts. One is based off an alpha of 0.3. The second is equal to alpha of 0.6. So again, we don't have a forecast for January 1995. That's the first period. In the second period, and let's look at alpha is equal to 0.3. Okay, so we have, again, the forecast is 97.6. So you see on the equation, the forecast of 97.6 plus alpha times 97.6 minus 97.6 gives you 97.6. Now, what about the third when the alpha is equal to 0.6? So you see here, we have the actual is 95.1. The forecast is 97.6. So for period number 3, that's going to be equal to 97.6 plus 0.6 times 95.1 minus 95.6. 95.1 minus 95.6, and that gives us a forecast in period 3 of 96.1. So you can see the equations on how this 97.6 and the 96.1 were calculated. So here is a graph for alpha, for the exponential smoothing. Alpha is equal to 0.6. Then alpha is equal to 0.3. And you could see the mean squared error for alpha is equal to 0.6 is less than the mean squared error for alpha is equal to 0.3. Therefore, in our study, an alpha of 0.6 would be more appropriate to use in the exponential smoothing. So let's go now and try an example. So you see the information there for weeks 1 through 7. We have sales of 39, 44, again, AT, so those are the actuals. So the first thing that we need to do then is to forecast for each period. And then you're going to compare the actuals to the forecast. So let me stop this. This data then is going to be transferred into an Excel spreadsheet. We want to create a forecast for week number 8. And since we have that data already, let's also create a forecast for week number 8 using a moving average. And I'm going to choose n equal to 3. There's no good reason for that. I'm just using that just to illustrate this process. Let's close this. Let's open up our Excel spreadsheet here. Go a little bit higher. So you could see there then that we have the formula for exponential smoothing and for moving average. For exponential smoothing, the alpha is going to be equal to 0.2. And for moving average, we're going to choose 3 periods. So again, we need a forecast for week number 1. So we're just going to choose, just to get the process started, we'll go out there and choose the observation for week number 1 as the forecast. Now, let's go out there and do a forecast for period number 2. So, how about this? Let me go over here and show you what the algebra would be. And again, we're going to be using the information from week number 1, to forecast week number 2. So algebraically, this is going to be equal to 39 plus alpha is 0.2 times 39, the actual minus the forecast of 39. And again, where did all this information come from? It came from week 1. AT is equal to 39. The actual is equal to 39. The forecast is equal to 39. So that's going to be a forecast. You can see algebraically, it's going to come up to 39. Okay, let's go out here and use Excel now. So let's program this in. This will be equal to the week 2 forecast will be equal to the week 1 forecast plus an adjustment for the error. So plus left 0.2 times the actual of 39 minus the forecast of 39. Right. This gives us a forecast of 39 in week number 2. Let's do this again for week number 3. So we're going to use the data from week number 2 to forecast week number 3. And again, this is going to be equal to this forecast, again, cell referencing, okay? Practice good programming, plus left parentheses 0.2 times left parentheses the actual minus the forecast. Right. And in this case then, the forecast will be equal to 40 for week 3 using exponential smoothing. So I'm not going to go through each one, especially since we can use the spreadsheet applications for Excel. So I'm just going to copy this down now because the formulas are correct. So all I need to do now, and the cell referencing is correct also. So all I need to do is just copy this down all the way down to our week 8 forecast. And in this case, using exponential smoothing, the forecast for week 8 is going to be equal to 40.5. Okay, now the question didn't ask for this, but now we have the data. Let's apply the moving average also. So we really can't, we have n is equal to 3, so we need sets of 3 to forecast. We don't have anything for number 1, 2, 3. But for week 4 now, we can take an average of the weeks 1, 2, and 3 sales and use that to forecast. So how about this? Let me do this. What's the algebra? This would be equal to 39. You could see it from here, the actuals, 39 plus 44 plus 40, right parentheses, divided by 3. Because n is going to be equal to 3. So we're going to use the actuals for weeks 1, 2, and 3 to forecast for week 4. And we're going to come up with 41. That's the forecast using moving average. So again, too tedious doing it the algebraic way. Let's use the tools that Excel gives us. So how am I going to make the moving average forecast for week 4 equals average, left parentheses, for these three, for B18 through B20. And it should come out to 40, equals average for B18 to B20. Oh, I'm sorry. I did the weeks. It should be the average based off 39, 44, and 40. So this is going to be the average of 39, 44, and 40, right parentheses. There's the 41 that we had calculated algebraically. And again, for the week 4 forecast, it's going to be based off this set of data. For the week 5 forecast, it's going to be based off this set of data. And for the week 6 forecast, it's going to be based off this set of data. All that has been carefully programmed into Excel. So I can now program into Excel into this cell. And again, using good programming practices, cell referencing, I can just copy this cell down and it will automatically calculate the moving average for me. So just copy this all the way down. And you can see that the forecast, the moving average forecast for week 8 is sales equal to 40. Sales equal to 40. So it's a little bit different than exponential smoothing. And again, what do you have to do? You want to, for either the exponential smoothing or moving average, you want to compare the actual to the forecast. That's for exponential smoothing. For moving average, actual to the forecast. Actual to the forecast. Whichever method, also, you're going to do that for different levels of alpha. Whichever method minimizes the error between the actual and the forecast is the preferred forecasting method based off time series analysis for your data. Now, I'm not sure what this is, but this could be sales of cars. This could be sales of cars. You have, and so right now, okay, 39 compared to 40.5 for exponential smoothing, 39 versus 40. Okay, it looks like if this was cars, moving average would be a better forecasting method. However, then you move to the trucks that your auto dealership is selling. Maybe exponential smoothing is a better forecasting for trucks. Then, again, I'm just making this up. Then you switch then to SUVs and exponential smoothing with an alpha equal to 0.75. That might be the most appropriate forecasting method. So there's a lot of analysis that needs to be done. However, use any of your software to assist you with the analysis. So there's still a lot of work to be done, and it's going to take some programming. It's going to take some programming, but It's much easier, obviously, than doing this by hand with a calculator. So let me get rid of this then. So I'm finished with this now. Let me save it. So this concludes this session with that about moving average forecast and exponential smoothing forecast. If you have any questions, please contact me. So again, this concludes this presentation. Thank you very much for watching.